Okay, question 3. So we've got some interference which is happening from a microwave transmitter. So we've got what is essentially a double slit experiment. And you can see from above here, they've got some path lengths from the two slits to some different positions of a receiver. So it says the microwaves from the transmitter are polarized. The waves are detected by the aerial in the microwave receiver. The aerial is a vertical metal rod. Okay, and we can see that it's moved along this line here, A to E. Okay, now the thing that is, you've got to read very carefully here. The receiver is moved along the dotted line. As it moved, maximum and minimum signals are detected. Maximum signals are first detected at points B and C. The next maximum is detected at D. So if you think carefully what's happening, we've got a maximum here. We've got another maximum here and another maximum here. Now, I think some people misread this and thought that this was a maximum and the C was a minimum. Okay, but it's not. So, I can't do that. So, C here is another maximum. That means in here somewhere, there's a minimum. Okay, so you've got to think about how many wavelengths of path difference are actually at play when we've got this, how many wavelengths of path difference you've got from the two slits. Right, now, figure 2 shows the distances between each of the two slits, S1 and S2, and the microwave receiver when the aerial is in position D. And it's basically just explaining the diagram. Explain why the signal strength falls to a minimum between B and C and between C and D. Okay, there are 3 things to say, and pretty much all of you wrote this nicely. So the first thing, got to tell the whole story, as always. Firstly, there is a path difference. Key phrase. Path difference for the two waves. That's the first step. That is the core of it all. That's what starts it, the fact that there is a path difference. What does the path difference give us? The path difference gives rise to a phase difference. Okay, so we can write phase difference. So the two waves arrive out of phase, and because they arrive out of phase, we get destructive interference. That's all you have to say. That is enough. So remember, look what it's asking. It says explain why it falls to a minimum. And so they're talking about destructive interference. So that's all you have to say, those 3 points. Okay, determine the frequency of the microwaves that are transmitted. Okay, so going back up here and back to what I was saying a moment ago. What is the path difference between S1 and D and S2 and D? Well, when the receiver was here at this position, this has gone from being in phase, going out of phase, and then getting back. That's out of phase here, or anti-phase, and then back in phase at C. Let me get rid of my marks here. So in phase, and then back in phase. So the path difference at position C is going to be lambda. That means if we go all the way out of phase and then back in phase a second time, that tells you that at position D, the path difference is going to be 2 lambda, because we've gone all the way out of phase, back in, and then all the way out of phase and then back in again. So that tells us this path difference in this arrangement is 2 times lambda. Okay, so let's write that down. They've given us, they've given us the path difference up here. So we can write down 2 times the wavelength is going to be 0.723 minus 0.667, which is 0.056, and that is in meters. So this is 2 lambda. Therefore, lambda is 0.028 meters, And of course, what kind of wave is this? This is an EM wave which travels at the speed of light. So what we're going to then do is we're going to use the wave equation. C is equal to F lambda. And that gives us our frequency. So the frequency is going to come out to be 11 times 10 to the 9. So I think some of you wrote 1.1 times 10 to the 10, which is probably more correct. In the mark scheme, it says 11 times 10 to the 9 for some reason. So that's it, simple as that. I think the tricky thing here was spotting the bit about the fact that it's 2 lambda. Okay, so some people made a bit of a, just missed that little bit, okay? All right, the intensity of the waves passing through each slit is the same. Explain why the minimum intensity between C and D is not 0. Okay, so let's have a look up here. What it's asking is at this position, let me get rid of this. What it's asking is at this position here, why do the waves not perfectly cancel out? So let's think about that. If I draw what it would look like, so we've got here and here, why do they not perfectly cancel out? If you think about two waves, imagine they were lined up. If they were going to perfectly cancel out, the amplitudes must be exactly the same, right? If the amplitudes are not identical, then they're never going to perfectly cancel out. And in the real world, often the amplitudes are not going to be the same. So if we think about this position here, why are the amplitudes not the same? Well, the distance to go from here to to S1, this is going to be longer. So the amplitude of the wave when it reaches this point is going to be lower than it is from S2. The wave from S2 does not have to travel quite as far. So when they meet, they do not have exactly the same amplitude. So let's go down here. We would say amplitudes from S1 and S2 are not equal. And why is that? Because, hang on, what's the because symbol? It's an upside down triangle, isn't it? Because they travel different distances. They travel different distances. It's a bit messy. Okay, so that is the answer there. So how many marks have we got? Yeah, it's only 2 marks. Okay, so amplitudes from S1 and S2 are not equal. They travel because they travel different distances. So we could probably finally say, therefore, they do not cancel perfectly. Okay, all right, that's enough for this one. We'll pick it up in the next one.